All right, welcome to week 3, lecture 2, in which we're going to investigate more pandas. Now, in the first round of pandas discussion, we introduced the series data type and talked a lot about how to interact with series. Now we're going to introduce the two-dimensional data type that pandas provides, which is called the data frame. All right, I'm gonna skip over these couple of reminder tests, and we'll get on to business here. So a data frame is a table, or you can think of it as being very similar to an Excel spreadsheet. Each column has a name. It's not technically necessary to give each column a name, but you should. And each row also has a label, which can either be a string that you provide, or by default will just be an integer index from 0 through whatever. So here is an example of creating a data frame from a dictionary. This time, our dictionary is going to contain keys, which will be the column names in our data frame. And we're going to have a list of values for each column. So instead of having a label and one value like we had in a series, now we're going to have a label, which is treated as the column label, and a list of all of the values that are in that column. That is, the list provides the values in the different rows. In this case, I'm going to create a variable for this table, T1, and so the name column is going to contain these three names, Smith, Jones, and Zhang. The age column will contain 42, 27, and 35, and the salary will contain the values shown there. And here's what T1 looks like. I didn't provide an index for this data frame, and consequently I got the default index labels of just the numbers 0, 1, and 2. You can also construct a data frame row by row rather than column by column, and we do this, for example, by creating a list of lists. Here is a list of lists. This actually contains the same information as our dictionary did, but in list form. I see. I have a typo there. So I'm going to copy this part and then append the 0, 0, square bracket, square bracket. All right, so the outer square brackets indicate that I'm creating a list, and within that list, I'm creating 3 sublists. Each sublist gives a name, an age, and a salary. All right, so there's my list. Now, to use that to create a data frame, I'm going to call this one T1A rather than T1. I can say PD dot, whoops, forgot my gets. PD dot data frame my list, whoops. And now, whereas in the dictionary, the column names were taken from the keys, here, since I'm using a list of lists, I have to specify the column names myself. So columns is gets name, age, and salary. And here's T1A, which is the same as T1. So you can see that we just used 2 different methods one involving a dictionary and the other involving a list of lists, to create these data frames. Yet another way of building a data frame is to use a list of dictionaries instead of a list of lists, or a dictionary of in which the values are lists. Here I'm just going to create 3 separate dictionary objects. All right, so I've got my dictionary object A. There's A. And then I've got a dictionary object B. Now notice that A and B have the same keys as each other, name, age, and salary, but different values corresponding to those keys. All right, and here I have a third one, C. D, now I'm setting up as a list containing those 3 dictionaries. D gets a list of ABC. Whoop, ABC. And here I can just create the data frame, and the data frame creation function will be smart enough to realize that each one of these dictionaries represents a row, and the keys within the rows represent the column names. The values represent the values that are supposed to go into those rows. And since the keys are the same for these 3 rows, name, age, salary, name, age, salary, name, age, salary, that means that I'm going to end up with 3 rows. I've got 3 dictionaries, and each of those rows is going to contain 3 columns. T1B, I'll call this, is pd.data frame from D. So here's T1, here's T1A, and here's T1B, and they all contain identical values, so we just created them in 3 different ways. All right, now if you would like to make a copy of a data frame, the simplest thing to do is to just use the copy method. So tcopy here is going to get t1.copy. Whoop, not copy, copy. All right, so T1 at this moment is the same contents and shape and so forth as tcopy, but these are distinct data frames from each other. I could test whether T1 is tcopy, and that's going to be false. Okay. Another way I can make a copy of a data frame is really just to create a brand new data frame using the p.dataframe creation function and give some data frame as an argument. In all of these cases so far, we have got our default integer values for labels. And it's likely that we don't really want that. So we can set a specific index, in this case, to replace the default index values, the default index labels 0, 1, and 2, with strings instead. And we're also going to throw in here the in-place equals true keyword argument, so that this happens in place within T1 as opposed to returning a modified copy of T1. All right, so let me copy and paste this rename code. All right, and I want to do in place equals true. All right, so we've seen this kind of notation before. You give the existing label and the new label that you want, specified as a key and a value in a dictionary. So I want 0 to be replaced with person 1, 1 to be replaced with person 2, 2 with person 3. And voila, it happens. And so now I have these string labels rather than just the integer labels 0, 1, 2. To access a particular row from the data frame, I can say t1.loc. You may remember .loc. t1.loc of one of these labels in square brackets. And so that will give me this particular row of values as a series. Okay, it turns out that when you request a row of values, you get back a series containing the name, age, and salary of that particular row. And notice that the column names are used as the labels for the values in this series. Okay, so here we're once again using data frame to create a copy. Not sure I don't think anything really new is being shown here because we already did a change of index on a data frame. In this case, we're just making a copy first and then changing the labels in the copy. I guess let me do it anyway just so that future examples will work correctly. All right, so I'm going to say new t1 is pd.dataframe built from t1. I could have said t1.copy equally well. What did I do wrong? Some silly typo. Oh! I've been writing C++ code today, and so that's a C++ comment. Let me try that again. Alrighty. So what I meant to do, of course, was this. Okay, £sign for my Python comment. And there we have it. So T1 is now a copy of, new T1 is a copy of T1. And now I want to change these rather impersonal row labels, person 1, person 2, person 3, to more personal labels, Bob, Mary, and Jay. So let me just go ahead and do that. I'll just copy and paste that whole thing. And poof. So new T1 now has the labels Bob, Mary, and Jay for these three rows describing these people. This is, this works. This is fine. It's a little bit risky because using first names as labels for people, if you have a whole lot of people and several of those people have the same first name, you end up with this problem of multiple identical labels for different rows in your data frame, just like we warned about having multiple identical labels for different values in a series. Okay, so this works fine here because it's a small data set and Bob, Mary, and Jay are different. If I don't use the in-place argument, then what happens is sort of what we would expect to happen. That is, the rename function is going to produce a modified copy of its data frame. It's not going to change the actual data frame itself. So here's T1, and if I say T1.rename index gets, this time I'm only going to change person 1 to Bob. All right, so that has the effect of only changing the label person 1. Wait a minute. Oh. Wait. Why did T1 change? So new T1 was created as a copy of T1. T1 changed. I don't quite understand why. T1A still has 0, 1, 2. T1 is, new T1 is false. So I wonder if somehow I made a mistake along the way somewhere and changed the row labels for both T1 and new T1. Interesting. Well, so instead of trying to change person 1 to Bob in T1, let me instead use T1A, which still has the value 1, and I'll see T1A dot rename index equal to, and here I'm going to change 0 to the string Bob. And that's all I'm going to do, and I'm not going to do that in place. So this does not modify T1A. This returns to me a modified copy of T1A. All right, so in this modified copy of T1A, the label 0 has been replaced with Bob, but T1A itself still has the label 0. You can do arithmetic operations on data frames, but you need to be careful about the data types of the columns. So if I say T1A times 3, well, doing a times 3 on a string means repetition, whereas doing a times 3 on an integer or a floating point number is actual multiplication. So we're going to get some potentially unexpected results here. All right, so notice that for the name column, if I multiply by 3, I get Smith, 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 Jones, 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 Zhang, Zhang, Zhang. The age and the salaries, those are properly just multiplied by 3. Now, of course, this does not change TA1 itself. If you add 2 data frames together that have the same rows and columns, that also works in the way you would expect. But if one of the columns is not numeric, then you may get surprised. So by adding the name of T1A to the name of T1A, again, I get Smith Smith for the first row and so on. These data frames that we've been creating are quite short, and so it's easy to see them entirely on the screen at once. But if you have a really large data frame, you can say something like T1A.head, and that will show you just the first 5 rows of the data frame, or T1A.tail, which will show you the last 5 rows from the data frame. Actually, T1A is not even 5 lines long, so I can abbreviate it even further by saying T1A.head, just give me 2 rows. All right, so I've got the names of the columns and then 2 rows of data. And of course, if you had a big data frame, you could say T1A.head 10 if you wanted to see twice the usual number of rows of data. Okay, now, if I say the data frame variable with just plain square brackets, I can give a column name, a column label, as an argument, and I will get a series for that particular column. Okay, so I said T1A sub age. Since age is a column name, I get just that series of age values. The data type of the elements in this series is int64. The name, of course, is age, and the labels are what they were from the data frame itself, 0 and 2. And similarly, I can get T1A of salary, and this is going to be a series of float64 values. We can prove that that's the case by asking to see what the data type is, T1A of, let's ask for the name this time. All right, so we see that if we extract a column from a data frame, that's given back to us as a series. And actually, the same thing is true if I ask for a particular row by saying T1A.loc of 1. That is also a series, but it's a series representing the rows. And notice that because these data types are radically different, NumPy that's containing the series sort of throws up his hands and says, well, I don't know how to convert these things all to be of a similar, or of a same type, so I'm going to just call them objects and not worry about it. But this also is a series. T1A.loc 1 is a series. Now, in the special case, I guess I skipped this, so let me back up a moment. Here's T1A again, as a reminder. These column names, fortunately, do not contain any spaces and do not contain any special characters like percent signs or slashes, which would mean modulus or division. So rather than saying T1A dot or T1A and then square brackets age, I can actually say T1A dot age as a shortcut. That wouldn't work if that column name had a space in the middle of it. Okay, in that case, you'd have to use the square bracket notation. Here, I'm doing what I previously referred to as fancy indexing. It allows me to select just certain columns, and for that matter, I can also change the order of those certain columns. So here's T1A, and I can select from T1A the salary column followed by the name column, let's say. Okay, and so that not only selects just certain columns, but also permits me to change the order of those columns. This is a new data frame, and so what's happening here on slide 16, although here we're using age and salary. I guess I should use age and salary to be consistent. I'm saying do I have a T2? No. I'm going to say T2 gets T1 with this fancy index of age first and salary next. So T2 now is a data frame. But just with those two columns. Here I'm adding together T2 to itself and storing the result in T3. We've already seen that you can add data frames together, so this isn't really anything new. I guess what's new is that since we do have only numeric values in here, the result stored in T3 makes better sense. The labels are the same, Bob, Mary, and Jay. Those are not like concatenated. The labels are just left alone as labels. But the ages and salaries are doubled. Okay. Now, loc takes a label for a row and displays the series for that row. I actually had previously demonstrated that. Let's compare and contrast here. So here's T1A. All right? And I can say T1A sub age to get the column as a series, or T1A dot loc sub 1 to get the first row as a series. Okay? If I have a data frame that does not have these integer labels as labels, let me go back to just plain old T1, in which our row labels here are Bob, Mary, and Jay. I can say T1.loc of J, all right, to get that row as a series. If I would like to refer to that row as the sub2 row, I can do that okay, but you may recall that we talked about iloc previously. So I'm going to have to ask for the iloc of 2 to get, well, interesting. Oh, okay, I guess in this example we just used Irene as the label rather than J. But in any case, loc takes a row label. iloc takes the corresponding integer subscript of that row label. All right, so T1.iloc of 0 would be a series representing the first row in the data frame, which in this case is Bob. Okay, I guess these are essentially the same as the examples I just showed you, so we'll continue on. Let me just summarize, because it is the notation does get pretty thick here. Here's T1. If I say T1 sub age, that notation is going to look for a column named age, and if that column exists, I will get the column as a series. If I say T1.loc Mary, all right, .loc means to look for a row whose label is Mary and show me that row as a series. And alternatively, I can say T1.iloc and specify the integer index of that same row. Okay, so T1 sub age is a column, assuming there is a column named age. T1.loc sub Mary is a row, assuming that there is a row labeled Mary. T1.iloc sub 1 is the sub 1 row, which in this case is the same as the Mary row. Now, T1 is an entire data frame. It has rows and it has columns. The columns have names, the rows have labels. We're accustomed, when we're thinking about this kind of information as a spreadsheet, to accessing a particular cell within this table by using row, comma, column. And .loc will allow us to do that. So I can say T1.loc and then give the row name, Mary, or the row label, I should say, followed by the column to identify the particular cell that I want. So in this case, T1.loc of Mary, comma, age gives me the 27. I have to give the row first and the column afterward. If I say t1.loc age and Mary, well, there is no row named age and there's no column named Mary, so I just get yelled at. Key error age. That isn't very friendly. So let's get that back. T1 t1.loc sub Mary, comma, age. All right. You can use iloc to select the row, but if you use iloc, you can't directly use the column name as the second index, let's say. So here, if I say t1.iloc, I can use 1, the subscript 1, as an alternative for Mary, but I can't also use age here. And you can ask why. Why is this? Well, just because. It's just because. So this won't work. All right. What will work is we can say t1.iloc sub 1. That will get the whole row for Mary. And then I can do a subscript on the age. All right, because remember that t1.iloc sub 1, that's a series, and I can access a particular value in a series by giving the label for that value in the series. Okay, so t1.iloc sub 1 is a series. t1.iloc sub 1 sub age is the age value for t1.iloc sub 1. These examples show other similar sorts of wacky combinations. I will leave you to explore those on your own if you're interested. But let's just move on, because this it's just bookkeeping. It's important to understand the general concept here, but you don't necessarily need to learn. Well, you might for the quiz. So try out each one of these combinations to see what's going on. Now, we've already seen the copy method that makes a full copy of a data frame. If you forget to do the copy and instead say some variable name gets some other variable name, that is going to simply create two references to the same data frame. Let me show you what I mean. So here's T1, and if I say x gets T1.copy, now T1 looks like it did, x looks the same, but T1 is not the same as x. In other words, the ID of T1 that uniquely identifies the T1 object is different from the ID of x that uniquely identifies the x object. Therefore, here's T1, here's x. If I say T1, let's say T1.loc of Mary, comma, age gets 29. All right, I have now changed Mary's age in T1 to 29. But that has no effect on x, because although x started out as an identical copy of T1, when I make changes to T1, that doesn't have any impact on x. However, if I say z gets x, now it's the case that z is x. They're really just two different names for the same thing. And so if I say z sub salary sub Bob. All right, in this case, Z sub salary is the salary column, and within the salary column, I'm asking for the Bob value. If I set that to, well, let me just subtract $2,000 from this poor guy. All right, so Z sub salary sub Bob minus gets 2,000. Hello. Value is trying to be set on a copy of it. Oh, yeah. Right. Right, because the minus gets there is equivalent to saying Z sub salary sub Bob Oh, I know what the problem is. I'm sorry. I know what the problem is. The problem is when I ask for Z sub salary, I get actually an entire copy of that. I get a copy of this salary column. I don't get a direct reference to that salary column. I get a copy of it. And so what I'm changing is a copy of that, and I really wanted to change Bob's salary, so let me use .loc instead. So I'll say, here's X, here's Z. They are the same. X is Z. And if I say Z sub Bob, comma, salary gets, or minus gets 2,000, hey. Oh. Oh, goodness, I'm such an idiot here. All right. All right. This time I made a different mistake. I forgot to say .loc in here. So we'll try this yet again, and this time I will fix that error. Z.loc. Okay, so now if I look at Z, I see that Bob's salary used to be $56,000, but I've reduced Bob's salary by $2,000. And unfortunately, if I look at X, I see the same thing because really X and Z are just two different names for that same data frame. So that's something that you really need to be quite careful about. Okay, now, it turns out that if you have an existing column, you can completely change all of the values associated with that column by just assigning some iterable of new values. All right, so here's T1, and I can say T1 sub age gets, well, let me say 27, 28, 29. All right, and so I have arbitrarily changed all of the values within age to 27, 28, and 29. Let me warn you that if you mistakenly just use a scalar, if I say T1 sub age gets 44, that scalar is going to be what's called broadcast across the entire column. So now everybody is going to have an age of 44. Let me put their ages back to what they were. Well, let me use the ages in the example on slide 24 here. So I'm going to say T1 sub age gets, what are this, 50, 65, 22. All right. You can also do a very similar thing to add a column. So in the previous example, I said T1 sub age gets some new values. But if I say T1 sub hired, Okay, and I'm just going to do this with T1. I'm not sure I even ever created Y. No, I didn't. So we'll just say T1 sub hired gets, and then a vector of years in which these people were hired. So 2015, 2010, 2018. And that just adds a brand new column, which is pretty cool. You can also add a new row by giving a new row label following .loc. So here's T1. If I say T1.loc of Bob, as we've seen, that gives us the row, the Bob row as a series. But if I say T1.loc of Fred, well, there is no row label named Fred, so this is going to produce an error, a huge long error. But if I say T1.loc sub Fred and give appropriate values, okay, Barnes 38 42750.0 and 2019. Okay, so if I say T1.loc of Fred gets these values, this is very similar to adding a new entry into a dictionary, where you would say dictionary sub key gets, and then some value associated with that key. Consequently, I now have T1 with this newly added row for Fred Barnes. We can use the append method of the data frame to append a row to the data frame. This version here doesn't modify the data frame itself directly. What it does is to produce and return a modified copy of the data frame with the row added. All right, so here I have T1, and if I say T1 dot, well, let me copy and paste all this stuff here, append name Gary, or name Gray, excuse me, age 50, salary, whatever, hired 2017, and ignore index equals true. So that means that we're going to add a new index value. We're going to add a new label, and that displays a modified copy of T1, but it doesn't change T1 itself. And in this case, there is no in-place parameter. So if we want to actually change T1 itself, we're going to need to assign back to the T1 variable the modified copy of T1. Okay, now the frustrating thing here is that when we do this, notice that we lose our original index labels. The original index labels here were Bob, Mary, Jay, and Fred, but because we've said ignore index, the new value just gets added in as item sub 4 or as row sub 4, and we lose our index. Okay, so I'm not actually going to do that. Well, okay. Now, you can use .iloc, as we've seen, to access a row of a data frame by treating the indexes, basically by ignoring the index labels and treating the indexes as though they were really just 0, 1, 2, 3, 4, and so on. But iloc will only succeed if the label already actually exists. So you can't add a row to a data frame by using iloc with an index that doesn't yet exist. That's not going to fly, so we get errors from both of these approaches. All right, so we can either use append, like we did here on slide 28, or we can use loc with a label subscript and new values for the row. In this case, we've got 4 columns, and so we've specified 4 values of appropriate types in a list. To get rid of a row, we can use the drop function. Let me illustrate that with dropping Fred from T1. And again, this doesn't actually modify T1. It produces a modified copy of T1. The drop function does take the in-place parameter, so I can say drop Fred in place equals true, and this will actually modify T1. You can also drop a column. Notice that for dropping the row, I put the label for the row in square brackets here. If you don't use the square brackets and you say T1.drop and just an ordinary string, well, a column name, and I'm also specifying access equals 1 to remember that we think of this conceptually as rows by columns. Rows are access 0, columns are access 1, and so that eliminates the hired column from the data frame. Once again, though, not modifying the data frame directly. So we can use good old in place true to accomplish that. All right, so let me copy and paste this, and again we'll say in place equals true. And that did modify the data frame directly. Okay, so this is a quite annoying thing that makes, when you can use in place and when you can't use in place. It's very difficult to remember because there's not a general rule for the various methods. Some of the methods take in place, other methods don't, and so you're forced, if you want to know all of these things in your head, you're forced to memorize which specific methods do allow you to say in place equals true and which specific methods don't. So I, frankly, tend not to memorize this stuff and instead, use Google to look it up in the documentation on a case-by-case basis. If you use something frequently enough, you can remember whether it takes in place or not. But if it's something that you don't do very often, it's not very easy to remember. Now, the transpose of a data frame is like the transpose of an ND array, the distinction being that the columns now have different data types within them. So the column for Bob in the case of T1.transpose, that ND array is going to be an ND array of objects rather than an ND array of strings. Likewise, Mary is going to be an ND array of objects, whereas age was an ND array of integers, and so on. Once again, this does not actually directly change T1. It returns the copy of T1 transposed. Now, you can sort the contents of a data frame in many different ways. Let me give myself back the row for J, or for Fred. The row for Fred. I want the row for Fred back. And I also want to put in the column. All right, so I'm going to put the row for Fred back. All right, so I've got the row for Fred back. I also want to get the column hired back. Actually, I guess, all right, if we look at the examples here on slide 33, I don't need that. So I've got Bob, Mary, J, Fred as my row labels. I've got name, age, salary as my column labels. If I say T1.sort index, that will do a default sort on the index values. Okay, the index values are the row labels. Okay, so remember, when we create a data frame, we can use index equals with a list to specify the row labels, or column equals with a list to specify the column names. So by default, when I say sort index, I get the row labels in ascending order. In this case, because they're strings, it's in ascending string order. That doesn't directly change T1. It just produces for me a sorted copy of T1. Now, if I want descending order, I can say, and this is weird, I think, ascending equals false. So by default, the ascending keyword parameter is true, but if I say ascending equals false, I'm going to get them sorted in reverse order. Once again, that doesn't actually change T1. It just gives me a sorted copy. But sort index is one of the methods that does take the in-place keyword option, so I can say in-place equals true if I want to save the inverted or the descending ordering of the labels. To sort the columns, well, okay, so we think of a data frame as being rows by columns. Columns is axis 1, rows is axis 0. So if I do this, if I say T1.sort index axis is 1, ascending is false, and I'm leaving out in place intentionally. Now I'm going to get the column names sorted in descending order. So I'll get salary, name, age. But that doesn't modify T1. All right? If I added the in place equals true, that would save the modification. All right, so sort index can be used either to sort the rows by labels or the columns by names. Sort values allows you to sort an entire data frame according to the values in some column. So here I'm saying T1.sort values by the name column. And by default, I have ascending, so I get Barnes, Jones, Smith, Zhang. And I can give the in-place parameter if I like. All right, so we've looked at many ways of creating data frames. We've looked at many ways of accessing the labels, the column names, the rows, the column values, the row values, the column values. We've seen how to change cells within by using dataframe.loc, and then in square brackets you give the row label, comma, and the column label, and you can assign a different value to that cell. We've also seen how to add rows, add columns, and eliminate rows, drop rows, and drop columns, as well as sorting. Once we have our information structured in the way that we want it inside of our data frame, we can do a whole variety of statistical operations on the data, similar to the kinds of things that we do in NumPy. And rather than sort of pre-describing these things, let me just show you several examples. Here's T1. And if I say T1.sum, what's going to happen is I'm going to get the sums of all the columns. I will get a series in this case in which the labels of the series values are going to be the names of the columns. So I'm going to get the sum of the names, the sum of the ages, the sums of the salaries. Now, what does the sum of strings mean? Well, it means to concatenate those things all together. All right, so we get Joan, Zhang, Barnes, Smith as the sum of the strings, 175 is the sum of the ages, and 202,775 is the sum of the salaries. If I want the sum of a specific column, I can choose, in the usual way, a column by its column name and ask for the sum of just that column. In this case, because there's only one column, I don't get a label, I just get the value, the scalar value of the sum of the ages. And similarly, I could do this for asking for the sum of the salaries. All right. I can get the mean of the columns, and mean is not defined for strings, but when I ask for the means of the columns in T1, I will get yelled at about the strings, and then I get the mean value, the average value for the age, and the average value for the salary. If I only wanted the mean value for a particular column, I can select it. So T1 sub age dot mean. This is because I'm asking for just one column, and because the mean function is defined over integers, I'm just going to get the mean value, 43.75, for that column. Here we're just showing an example of how you can take that individual value that you get from mean and display that in a nice formatted way. T1.describe produces various summary statistics for the whole data frame, excluding the column containing strings. So here I have the number of rows in which age is specified, so that's the total number of rows in the data frame. I get the mean value, the standard deviation of the values, the minimum, the maximum, and then these 25, 50, and 75% quintiles as well. if I would like to get just one. Now, notice that this result here is a data frame. So if I ask what the type is of t1.describe, okay, it is a data frame. Age and salary are the column names, but these labels down here in the left side, these are row labels: count, mean, standard deviation, etc. So I can ask for t1.describe .loc of the mean row resulting from describing, and what I get is the ages mean and the salaries mean, okay, as a series. I can get the maximum. Let me redisplay T1. All right, I can get the ID of the minimum record for salaries. All right, so here I'm asking for T1.salary. That's going to be the column of salaries. And if I ask for T1 sub salary dot ID X min, well, let me just show min first. Here's the min. All right. And if I ask for the index min, I get told that the label, the index of the row that has the minimum value is Mary. Now, in the slides here, this version of T1 has integer row labels, 0, 1, 2, 3. But in my case, my version of T1 has strings as row labels. Similarly, I can ask for the ID of the maximum, which is going to be J in my case. Okay. Okay, so now here we're using that label, that row label of the row with the maximum age, and we're using that as an index into the data frame itself. So let me do this with salary. All right, so we know that J is the label of the row with the maximum salary, so I can say t1.loc of J, and that's going to give me the row describing J. So give me the entire row for the person who has the maximum salary is basically what this is saying. And so I get the name, age, and salary values for J. All right, so name, age, and salary values for J. Hey, now this is unfair that this 22-year-old has the maximum salary among these people. Perhaps you don't think it's unfair. And we can, carry on with this. Here we're just asking for the name part of that row. Pandas provides a whole bunch of read functions for reading in data frames from a variety of different kinds of files. We can read from a CSV file, read from an Excel spreadsheet file, read from an HTML table, or from JSON, or from Pickle. And there are many keyword options that specify details of how to interact with the contents of these files. For example, if I say pd.read CSV, let me scoot this up a little bit because it's probably going to go off the bottom of what I'm recording here. So if I say read CSV and hit the parenthesis, you can see there's this tremendously long list of options that you can specify to indicate where in the file the column names are, where in the file the row labels are, what should be done with missing values in the file, how quote marks, how double quotes or single quotes in the input file should be handled, whether dates represented in the file should be interpreted as strings or as the date data type, on and on and on and on. So you really have to read the documentation to experiment with and try out all of these different possibilities. Well, I'm not going to. Come here. Okay, I gotta make that go away, and I'm gonna grow my window again. Hey, why can't I? Boy, my mouse is being flaky here. Wow. All right, I'm gonna give up. Maybe I can grab by the corner. There we go. Grab by the corner. There we go. Okay. You can also write information to these various formats. For example, if I wanted to write this data frame into a CSV file, I can specify the path where the file is located. And then once again, I have a whole bunch of options that I can use to specify the internal formatting of this text CSV file that I'm creating. I'm not going to actually do these, but here are some examples. Let's suppose that this is the contents of a CSV file that we have. All right, so we have 4 column names here: date, team 1, team 2, and score. And the date here is, in the file, it's just a string of characters. Well, of course, everything in the file is just a sequence of characters. So I've got date represented as month, day, year. I've got the team, football teams in this case, the home team, team 1, and the visiting team, team 2. And then I have the score for the home team and a dash and the visiting team. By default, when I read this in with read CSV, notice that I didn't specify any row labeling, and so the row labeling by default just gets set to 0, 1, and 2, which is fine. Perhaps I want to treat the date as a column and team 1 and team 2 and scores as columns. But let's suppose that I wanted to have the date treated as the label. Well, in that case, oops, I was sure that that example was happening next. I could specify the column that I want to use for my labels as an option. Once I have read in the data frame from the comma separated value file, I can do the usual kinds of things. So scores.iloc sub 2, that's going to access this sub 2 row. And within that sub 2 row, I can access any column that I like by using a subscript and a column name. So here I'm accessing team 2. And here I guess we have an editorial comment from Professor Barrett. So I guess he doesn't like the Browns, and so he's renaming the Browns to Poopy Heads. And then we're writing that back out into a file called new scores. All right, so now if we write that out to a CSV file and read it back in, we now have the poopy heads rather than the browns. If you're not from around here, which I know many of you are not, the Browns are the team that the Steelers most hate, or perhaps we should say that Pittsburgh and Cleveland have this sort of imagined rivalry, and so we're required to hate each other's football teams. Okay. Well, here we have another couple of examples of saving information into and reading information back from CSV files. If you want to read in a CSV file and you do want one of the columns to be treated as the index column, that is the column containing the row labels, you can specify the index column by integer subscript. So we started out with our CSV file looking like this. And let's suppose that we did want to use the dates as labels. We could have said pd.readCSV, scores.csv, comma, and then index underscore call equals 0, and that would have caused the dates to be rendered as the labels, and the columns containing data would then have been team 1, team 2, and score. You can try that out for yourselves. Okay, well, that is the conclusion of all of the data frame material. And perhaps I will see you today if you're willing to brave the bitter cold rain. But you're welcome not to come to the lecture and instead to view this YouTube video. All right, take care. Bye.